All right. Hey, welcome, AP Stat personnel, students, ladies and gentlemen. Um, hey, here's our first of, I think we're going to do two videos here. Yes, two over chapter 12 to finish up the curriculum. Yay. So that we can move forward with AP review and getting ready for AP exams, whatever those may look like. All right. So, hey, I'm not just a pen and a hand. So let me just say hello real quick. Hello. How you guys doing? Um, so in chapter 12, get a little bit closer here. We're going to take some of the concepts with regard to linear regression and how to look at and create and assess a linear model between two variables and kind of take that a step further and say, okay, is there a way to maybe do an interval or a test to see if we have convincing evidence of an association between two quantitative variables? All right, so we're going to take the whole concept in chapter 11 with chi-square tests of association, which was for categorical variables, and look at how to do the same type of thing for quantitative variables. And slope's going to be the key there. All right, so if you look here on the first page of the chapter 12 notes, get a little closer, you'll see that they've got a linear model represented here. So this is the duration of an eruption for Old Faithful and looking at how that relates to the interval before the next eruption. Okay. So these are all the data points for eruptions of the Old Faithful geyser, all right, which is in Yellowstone National Park, over the course of a month. And so they're going to call this a population, entire population, this month worth of eruptions. So we're just going to consider our population to be 1 month worth of data. So because it's an entire population, we can deal with parameters instead of statistics. All right. So you can see here that when they write an equation for a line of best fit, we're no longer using predicted y and x and stuff like that because we're talking about the population. So we're talking about the true mean of the y's is equal to alpha, which is going to be the true standard deviation, I'm sorry, the true y-intercept plus beta x, where beta is the population slope. All right. For this particular data, they're telling us that, okay, the mean of the y's for a particular x can be defined by this linear equation. All right, where 33.35 is alpha, your y-intercept, 13.29 is your slope, beta. All right. So given all of that, if we want to do inference about slope, just like we did inference with means and inference for proportions, all right, confidence intervals and tests, we need to know what the sampling distribution looked like first. All right, because that gave us basically a way to check our assumptions and go forward from there. All right. Okay, so now here they're talking about doing a simulation to see what that sampling distribution looks like. Time certainly does not permit us to do that, but what we could do is say, okay, from these 263 points, take a sample of size 15, X and Y values, put that into list 1, list 2, those 15 data points, do a linear regression, get a line of best fit for that sample data, and then take the slope out of that, B, okay, and then do that over and 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 over again to simulate a sampling distribution. Okay, so that would be the idea there, but we're not going to actually do that there. We're going to actually just go right in and show you what the sampling distribution for slope would look like. All right. And again, this is going to help us with conditions when we do inference for slope and things like the standard deviation, standard error formulas and stuff like that. All right. Okay. So nothing really to write down on this first page, just kind of an introduction of where we're at. For inference for a slope, we're going to take a sample slope from one sample, and we're going to try to either using a confidence interval, make an estimate of the true slope, or using a significance test, see if we have convincing evidence of an association between the two variables. All right. Before we get there, an association between two variables. So if we have a slope that's either positive or negative, then we have an association. But what does no association look like? Well, that's flat, right? That means regardless of whatever the x value is, the y value really isn't affected by that. It doesn't change. All right. So no association in terms of slope is going to be a slope of 0. All right. And we'll get to all that here in a minute. Okay. Let me switch over to the next page. Okay. Oh, no. Sorry. That's the previous page. Okay. So when conditions are met, describe the shape, center, and variability of the sampling distribution of the sample slope. So for that question, it's laid out pretty well here in the textbook. You switch over to that. This is on page 741. Okay. Sampling distribution of slope. Okay. So it tells you right here, so for center, spread, and shape of the sampling distribution, the mean of the sampling distribution of slope is simply the true mean, or the true slope, beta. The standard deviation of the sampling distribution looks like a complicated formula there. So the standard deviation of the slope is equal to the standard deviation of the residuals. And again, this is the population standard deviation of the residuals because it's sigma, over the standard deviation of the x values times the square root of n, which is the sample size. All right. Always with standard deviation formulas, those hold as long as the 10% condition is satisfied. All right. Okay. And then the sampling distribution of B will be approximately normal. Okay. This is going to kind of work like t-tests and t-distributions. If the values of the response variable follow a normal distribution for each x. Okay, so there's a normal condition that we're going to check. It's going to look a little different than past normal conditions, but if all that's true, then we can use a sample slope to make some predictions or do inference about the true slope. Okay. All right, so if we jump back to the notes real quick, it's a little dark, but can't help that too much. Okay, so this is just basically what you saw in the textbook. All right, for the center, all right, the mean, the sample slope is equal to the true slope, beta. For spread, you have that kind of wild formula. Now, you're not going to have to worry too much about this formula, but the standard deviation for slope is equal to standard deviation of the residuals over standard deviation of the x values times the square root of n. We just saw that a minute ago. And the shape, if all conditions are met, is going to be approximately normal. Okay. All right, next question here says, and if you just look at the formula, the spread formula up here, what factors affect the standard deviation of the sampling distribution of the sample slope? Say that 5 times fast. And what if we don't know the true standard deviations? Okay, well, if you look at the formula, all right, what affects the spread for slope is really everything you see in the formula, right? So the factors would be sample size, standard deviation of the residuals. And if you think back to chapter 3, when we talked about S and we interpreted S, the standard deviation of the residuals from a sample, this is just the population standard deviation of the residuals. All right. And that kind of assesses to some degree the fit of the line, how well it fits the data. And then also standard deviation of the x values affects the standard deviation of slope. All right. So it's kind of standard deviation of residuals. Remember, residuals are the up and downs from the line. So that's kind of where the y's are represented. Here's the standard deviation of the x's. So both of our standard deviations of our two variables are represented here, and then the sample size. Okay. All right. What if we don't know the true standard deviations? Then we must use, this will look funny, but the s's, all right, which are the sample SDs. And if you remember back to t distributions in chapters 7 and 8 and 9, because we're using a sample standard deviation instead of the true standard deviation, sample standard deviations are always going to be a little bit less, or maybe quite a bit less than the population standard deviations. And so we need to account for that when we do our inference procedures. So we are going to use T procedures, which do account for that. Okay. All right, so that's where we're going there. All right, so next question is, what is the regression model when the conditions for inference are met? Okay, and this is going to kind of lead us into what our conditions need to look like. All right. Let's look at the picture. Might help here. This is on page 742. Okay. All right. And so kind of where the conditions are going to come from are the thoughts that you see here in this picture. So if you look at the red line, okay, that is our population LSRL. Okay. And so if we look at that, for each of the X values, notice that the Y value should be approximately normal. So you see a bunch of approximately normal distributions there for each X value. All right. So that's one thing that that will be true if the conditions are met, and that will be one of our conditions that we'll check here in a second. Notice that the means of the Y values for each X are on the line of best fit on the LSRL. Okay, you can see that here. Here's the mean of this distribution, the mean of the Y values for this X value. Here's the mean of the Y values for this X value, the mean of the Y values for this X value, and notice they all fall on that line. Okay. Since we have normal distributions, notice that for any X value, the spread should also be pretty standard. Okay, so notice that the standard deviation is the same for each of these normal distributions. All right, so really along this population line of best fit, you just have a series for each X value of normal distributions with the same standard deviation, different means obviously because these values are going up here, but the spread should be about the same for each X value. All right. And then, like I said, normal distributions for each. Okay. So when we talk about the regression model here, again, we're just going to put that to paper here. So for each X, the intervals, we'll call it the distribution of the Y values, should be approximately normal. Okay. The means of the Y values for each X should be on the LSRL for the population. All right. And then the last thing that we talked about is the spread of the Y values for each X should be constant. And those are the things that that picture showed us there. Okay. All right. So if we go back to the Old Faithful data, how could we use the sampling distribution to answer a question like this? Okay, let me move this up. Okay, so there's that same population LSRL. They're telling us that the standard deviation of the residuals is 6.5 as well. Okay, so assuming that the regression model is valid, okay, and we're going to get to conditions in a minute for how to check that. The question here is, and it's a sampling distribution question like we saw in chapter 7, is that assuming that model is valid, for eruptions of 4 minutes, how often will we need to wait more than 90 minutes until the next eruption? So what is the probability that we'll need to wait more than 90 minutes until the next eruption? So if we first plug 4 in for x, for duration, into the equation, we get mu y equals 33.35 plus 13.29 times 4. Let me do the math real quick in my head. Okay, 86.51. All right. So that should be our what we would say the duration is, okay, using that model, if the last eruption was 4 minutes long. So in other words, if Old Faithful went on for 4 minutes, its eruption, then we would have to wait 86.51 minutes until the next eruption. That's what that model was trying to tell us. Okay. All right. So 86.51. What does that look like as a z-score? Okay. I'm sorry. What does 90 minutes look like as a z-score if the mean of our y values is 86.51? All right. So this is kind of the center of our distribution, right? Okay. So if we convert 90 minutes, okay, so that's the duration they're talking about. What's the probability that our duration would be more than 90 minutes? Okay, probably a pretty high probability. Well, maybe. This is 86.51, which is pretty close to 90. So if we convert that to a z-score, the 90 minutes, we'll do 90 minus the mean of the y values for a 4-minute eruption. Divide that by the standard deviation of the residuals, in this case, which is 6.5, and we get 0.537. Okay. Then we can do a real simple normal CDF type probability. So what's the probability that our duration is greater than 90? And that would be the same thing as the probability that our z-score is greater than 0.537. And we can use normal CDF to answer that question. So our lower would be 0.537, which is the z-score, and our upper would be infinity. All right. And if we do the math, if you put that in the calculator, you get about 0.296, which would be the answer to that question. Okay. About a 30% probability that the next eruption would be 90 minutes or more after the one that took 4 minutes. Okay. So again, here we're just taking the linear model to get our y value, all right, the mean of our y values, and then to answer the question, we'll take the value of interest, which is 90 minutes, convert it to a z-score, okay, using that mean and that standard deviation. Again, sigma, it's the standard deviation of the residuals, but that also is really the standard deviation of your y values as well. All right, and then that gives us the z-score, and then we can just go from there. Okay, so you may or may not see a sampling distribution problem on a quiz or a test with regard to inference for slope, but that's how you would address something like that. Okay, all right, so let's next go to the conditions for inference. Okay, so I know you guys love checking conditions. You're really going to love checking conditions in this case. All right, so we're going to use an acronym called LINER. L-I-N-E-R. So technically, instead of 3 conditions like you're used to for the types of inference we've done in the past, now there's 6 conditions, all right? But this isn't going to be that hard, okay? It's really just a matter of looking at graphs that you'll have in front of you and stuff like that. So, okay, so let me show you what the conditions look like in the textbook because it's a lot easier to read. All right. Whoops, it's our sampling distribution. Conditions for inference. Okay. Here they go. And there's your LINER. Okay. So N is the number of dots, basically, observations on our scatter plot. Okay. And our goal is to predict Y from X, right? So in order to do inference for slope, all of these have to be true. All right. One of them is pretty obvious. It's something we've been looking at all along. The relationship has to be linear. A linear model must be appropriate. Okay. How do we check that? You already know. No pattern in the residual plot. Scatter plot looks fairly similar. Okay. But the residual plot's really your source for L. All right. For I, that's the 10% condition. All right. We need our observations to be independent of each other. So if you're sampling without replacement, we want to check the 10% condition here. Otherwise, you can skip it if the data comes from an experiment. The normal condition, if you think back to that picture we looked at earlier, what it said is for each value of X, the Y values need to vary normally, all right, have a normal shape, okay? We'll write this down in a minute, but what we'll do is look at a histogram of the residuals and look for any strong skewness or outliers. It'll be as simple as that for the normal condition. All right, for equal SD, we talked about this. For each X value, we would want the spread of the Y values to be pretty constant. The residual plot will tell us that. We'll talk about that here in just a second. And then the random condition, which you know about, all right? Data has to come from a random sample or a randomized experiment, okay? All right, so let's get a little bit more specific about how to check those conditions, okay? All right, so for L, which is linear, all right, we want in the residual plot, and residual plot is always better than the scatter plot for checking linearity, all right? Okay, so we want no obvious curved pattern. Okay, you could also look at the scatter plot, all right? It should have a reasonably linear form. Sometimes that's kind of a guess on the scatter plot, but that's why we use the residual plot. Okay, all right. So linear, you're used to checking that already. That's the same check. For the independence condition, it's the 10% condition. As easy as that. Skip if it's an experiment. In the normal condition, this one's going to be a little bit new. Okay, so we're basically saying the Y's for each X are approximately normal. So to check that, we're going to look at a histogram of the residuals, okay? When you do a linear regression, you create a list of residuals, so you can certainly do a histogram of them. Normally, this will be a graph that's provided to you, okay? When we look at it, just check for no strong skewness or outliers, like we do in the normal condition for means when we have to graph the data, okay? All right, E is, again, that's the equal SD condition, all right? Meaning the standard deviations of the Y's are pretty constant for each X, all right? And so for that, so constant SD for each X. So for that, we're going to look at the residual plot. And we'll see examples of all this here in just a second. So the residual plot values are fairly equally spread around the zero line, which is that horizontal line in the middle, for all the x values. Okay, and again, we'll look at an example in a minute. Where this condition wouldn't be met if, like, you looked at the residual plot and it, had sort of a cone shape. If the dots are pretty equally spread, and when I say spread is the distance from that zero line on the top and the bottom, if it's pretty much the same for each x, if you go across horizontally, then this condition is met. All right, and then the random condition, you know how to check that. Random sample or random assignment. Okay. All right. It's probably the least fun thing about this process is checking the conditions. All right. Okay. Let's move on. Okay. So if we are going to do inference for regression, okay, there are actually three different parameters that we could do inference on. Okay. We're only going to worry about one. Okay. But if you wanted to, you could do inference on alpha, which is the y-intercept, sigma, which is the true standard deviation of the residuals, or beta, which is the true slope. Okay. Since slope tells us association between two variables, all right, we're only going to focus on this. All right. But just so you know, we could do inference using those same conditions on the other components of an LSRL as well. Okay. All right. Standard error of the slope. Okay. You're going to be happy about this ultimately because really this value is going to be given to you. You'll see it in the computer output, which is so wonderful that they give us on a lot of these types of problems. All right. There's a formula, though, that comes up, and especially in multiple choice questions, you want to be familiar with this. Okay. So the standard error of the slope is equal to, all right, and so with standard error, we're using sample data to compute it, right? That's why it's called standard error instead of sample standard deviation. Okay. So the formula for that is the standard deviation of the residuals, S, you're familiar with that, divided by the standard deviation of the x values, you're not familiar with that, divided by the square root of n minus 1. All right, so similar to what we saw earlier, but this would be the standard error. Okay. All right. Is it on the formula sheet? Yes, it's on the formula sheet. Okay. But you won't use this often. Okay. Standard error of the slope will be in the computer output. We'll talk about that later. Okay. How do we interpret it? Like any standard error, we could say if we take repeated samples, it is the typical distance between the estimated or sample slope and the true slope of the true regression model. Okay. That's always how we interpret standard error. Let me align that a little better. Okay. All right. So that is standard error. We will look at specific problems where you will have to compute it, but again, that's going to be pretty straightforward ultimately. Okay. All right, so as you saw at the top here, we're looking first at confidence intervals for slope. How do we estimate the true slope of a linear model? Okay, so we need a formula for constructing the confidence interval for slope. So let me write it here. It's really easy. Okay, we're going to take the sample slope, which is little b, okay, plus or minus. Since we're using t procedures here because of estimating standard deviation using sample standard deviations, we're going to use a t critical value here. All right, and then we're going to multiply that times the standard error of the slope, which we just talked about a minute ago. So that's your formula for a confidence interval. Okay, now for inference for slope, since we have two variables, degrees of freedom is always going to be equal to n minus 2. So the number of observations, number of dots, minus 2. Okay? All right. The t-critical value does not come from the computer output. We will have to compute that. I'll show you why that may be confusing. If you look at the computer output in this next example that we'll get to, you'll see a t, all right? But that is a t-test statistic, not a t-critical value. So don't confuse those two things, okay? All right, so that is our formula for the confidence interval, okay? All right, so that takes us to an example. Now, before we do that example, let me run through an example in the book to kind of give you a little bit better context here. And I'm just going to, kind of page through this real quick. And so the helicopter one, it's the car one, which is, we already did that. Okay, I believe this is it right here. Nope, that's helicopter. It's this one. Okay. All right, so we've actually looked at this example before. How much is that truck worth? So back in chapter 3, we looked at this, the relationship between how many miles an F-150 is driven and what it's worth. All right, obviously, this is a negative relationship. The more miles on the car, the less it's going to be worth. That should make sense, but we can represent that with a linear model. Okay, here's all the sample data. And so what they did for us is a scatter plot. Okay, so you can kind of see the negative linear relationship here. Notice we have a couple of clusters, it looks like, maybe something to note if you were describing it. And then we have a residual plot over here next to it. Okay, and again, this is going to be standard form of operation. You're going to be given basically everything you need in terms of graphs on the AP exam and on just about all test questions. Okay. So notice there's really no obvious curve pattern. On some of the chapter 3 homework, I saw a couple instances where people were trying to maybe come up with a curve pattern or say there's a curve pattern. It should be very obvious that all the dots make a U or an upside down U or, maybe some sort of exponential look or something like that. If you don't see an obvious curve pattern, then we're good enough using a linear model, okay? Now, we'll get to this here in a second, but when we talked about conditions and the equal SD condition, that would mean as you go across left to right for each X value, the residuals are about the same spread, okay? And they really are here, okay? So it's going to meet that condition, which we'll talk about in a minute, all right? If the dots kind of went down here like this and kind of went down here like this, and all of these dots were a lot closer to the blue line than these were, then that would be an instance where the equal SD condition isn't met. Okay, all right. So for this condition, they also give us a histogram of residuals. And so for our normal condition, we're just making sure there's no strong skewness or outliers here. Certainly not. Here's our computer output that gives us information about the line of best fit, S, R squared, etc. There is some additional information here that we'll use. If you look at the slope, which is this number here, negative 0.16292, right next to it, where it says under the column SE coefficient, standard error of the coefficient, that is the standard error of the slope, okay? So we're going to pull the standard error of the slope right off of the computer output, okay? T, when we go to do tests here a little bit later on in this chapter, we can make use of t, but that doesn't apply to a confidence interval. Okay, so if we construct and interpret a confidence interval for the slope of the regression line, okay, here's our state step. In the plan step, conditions are met. The inference procedure name here is a t interval for slope. Okay, if you want, you can just write t interval for slope, but that is going to be the inference procedure name for this. And then we go ahead and do liner, the conditions. All right. So linear, we saw this earlier, no obvious pattern in the residual plot. I don't know that I would even mess with the scatter plot. We're checking the linear condition. The residual plot tells us really all we need. If there's no clear pattern, we're good. For the 10% condition, so if we go back to the beginning of this problem, this is sample data. It wasn't an experiment. They sampled different trucks and got information on how many miles they were and what they were worth in Auto Trader. This was not an experiment. So we do need to check the 10% condition. The number of values, sometimes that's hard to see. If you're given the data, there's 1, 2, 3, 4, 5, 6, 7, 8, looks like 16 different dots, and you can count the dots here as well. So if we do 10 times the sample size, 16, that's 160. Is it reasonable that the population of Ford F-150 Super Cruise is greater than 160? Absolutely. So the 10% condition will be met here. For the normal condition, okay, histogram of the residuals right here, no strong skewness or outliers, and we're good there. Equal SD, the scatter of points around the residual line appears to be about the same for all the X values. Here's the residual plot. That does appear to be true. And then we randomly selected the 16 pickups. You should pull that out of the problem statement. And so our conditions are met here, okay? If we go to the do step, okay, we have to do inverse t using n-2, which would be 14 degrees of freedom to get the t critical value. So inverse t, area to the left would be 1 minus the confidence level divided by 2. So it would be inverse t of 0.05, and then comma, degrees of freedom 14 would give you 1.761 for the t critical value. All right, here's the sample slope, negative 0.16292. That is straight off of the computer output right here, sample slope. And standard deviation, 0.03096, also right off of the computer output. It's right next to the slope there. You see that, okay? All right, so we just use the formula using those values to create our confidence interval. There it is. You can use technology if you have the data. That's not really going to be the case very often. We'll look at that at the very end of this particular packet, but you're going to actually probably use the formula more often than not when doing a confidence interval for slope because you're not going to have the data. All right, and then just our conclusion statement for a typical confidence interval. We're 90% confident that the interval from blah, 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 to blah, blah, blah captures the true slope of the population regression line, okay, because we're estimating the slope of the population regression line relating, in this case, price to miles driven. All right, so there you go, good example there, okay. All right, so if we go to the example in the notes, okay, this one is looking at the relationship between how long people stay at an Asian buffet and how much they tip, okay. So you can see the scatter plot here. All right, here's time at the buffet. Here's the tip amount, okay. So it looks like, yeah, potentially a linear model here. The line of best fit's drawn in there. Doesn't look real strong, right? Looks like the points are pretty scattered there. Right next to it, you have the residual plot. I don't see a strong curve pattern or an obvious curve pattern, so I think a linear model is okay. All right, don't confuse the fact that a linear model is okay versus the strength of the linear model, okay? If you look at R squared here, that's pretty low. So this is not a very strong correlation, or this wouldn't associate itself to a strong correlation, but a linear model is still appropriate because there's no obvious pattern in the residual plot. All right, there was some confusion on that in chapter 3. Okay. All right. So what is the equation of the LSRL? Okay. So we're talking about predicting the tip. Okay. So it says define any variables you see. I think it's easier just to write the variable context within the equation itself. All right. Okay. So this information is from a sample. So we're talking about predicting the tip. So predicted tip is equal to the y-intercept is 4.535 plus, because the slope is positive, 0.03013 times, what's our x here? It's time at the buffet. Okay. All right. So there's our LSRL with the equation, or with the variables defined, and our hat like it needs to look. Okay. So moving on. Okay. So part B, part C, both of these are chapter 3 review type items. All right. I would encourage you to stop right here and go ahead and write those interpretations and come back and check this. All right. But you should be able to handle that. Part D, interpret the standard error of the slope. We talked about how to do that a minute ago. Part E, we're actually going to do a 95% confidence interval with the 4 steps, and then do a follow-up example in F. All right. Okay. All right. So you're back. Okay. All right. So here's what your interpretation should basically look like. All right. For slope, for y-intercept, make sure you're using the word predicted in there. You will get marked down if it does not indicate that we're talking about the predicted increase or decrease, or the predicted y-intercept value. All right. And you should have noted that in some of the comments if you left that off on the homework or the quiz for chapter 3. All right. And then for S and R squared. So for interpretation of S, make sure you put in here something about when using this LSR to predict y from x in context. That does need to be there. And for R squared, you have to have approximately in front of the R squared value, because it's not ever going to be exactly 13.2% of the variation or whatever it is. Okay. So just a couple of common errors on those interpretations I wanted to point out. Okay. All right. So moving forward a little bit. So for interpreting the standard error of the slope, we did a little template of that a minute ago. Okay. So if we take repeated samples, okay, our sample size here was 12. So with 12 receipts of the Asian buffet, the estimated or sample slope will typically vary from the true slope by about, and then whatever that value is. Okay. Now in this case, if you go to the computer output, which I have right here, 0.024 is the standard error of the slope. It's right next to the slope itself, just to the right of it. So there's where we got that 0.024 number. Okay. All right. Then calculate and interpret a 95% confidence interval for the slope of the population regression line. Okay. The state step. Okay. We want to estimate the true slope beta of the, or I'm sorry, estimate the slope beta of the true regression line relating time at buffet to tip with 95% confidence. Okay, so that's what our typical state step is going to look like for slope. For the plan step, we want to write our inference procedure name and check our conditions. Okay. So if conditions are met, we will perform a t interval for slope. For the linear condition, if we go back to our graphs, no obvious curve pattern in the residual plot, so we're good there. Okay. The scatter plot also shows a somewhat linear form. Okay. But you don't necessarily have to mention the scatter plot when you check the linear condition. For the 10% condition, our sample size was 12 receipts. So the population of receipts at this restaurant can be assumed to be greater than 10 times the sample size, which was 120. All right. For the normal condition, the histogram of the residuals needs to have no strong skewness or outliers. Okay. And it doesn't really have strong skewness. I know you might argue that it's a little bit skewed left, and maybe it is, but there's certainly no outliers because you don't really see any gaps here. There's really just a couple of values that are a little bit lower on this end. So again, we're pretty conservative with our no strong skewness and outliers like we are with the dot plots. It really has to be obvious for that condition to fail. All right. Then the equal SD. So the variability of the residuals in the residual plot is reasonably constant for all the X values. That's really all you're looking for. All right. And again, if we look at the residual plot here, as we go left to right, the spread across this middle line, the zero line, is fairly constant. Again, it needs to be pretty obviously off for that to fail. Okay. All right. And then the random condition, it was stated in the problem. All right. So for the do step, we just use our formula. Okay. If we do inverse t, we're doing a 95% confidence interval, so we would do inverse t of 1 minus 0.95 divided by 2. And then degrees of freedom would be 12 minus 2, which is 10. Okay. And then, so that gives us our t critical value. And then here's our slope, plus or minus t critical value. Here's the standard error of the slope. Again, coming right off of the computer output right here. Okay. And that gives you this confidence interval here. Okay. Conclude statements, our typical conclusion statement for an interval. Again, we're trying to capture the true slope of the regression line relating time spent at the buffet to tip. Okay, so that's what your conclusion would look like. Is there convincing evidence of an association? Okay, well, so a slope of 0 would be no association, right? Because that's a flat horizontal line. So if you look at our interval here, 0 is actually contained within this interval because we have negative positive, all right? So since no association is plausible, we would have to say no here, okay? 0 is within the interval, so 0 is plausible, no association is plausible, so there is not convincing evidence of an association, okay? Pretty similar to some of the previous problems that you did with regard to that, okay? All right, awesome. Okay, so let's move on. That is a confidence interval. Okay. What about a significance test? Okay. All right. How do we do a significance test for slope? Okay. So again, the basics of this are going to be pretty similar to what they were for confidence intervals. Okay. What's different about a test, a significance test, is we have a test statistic. All right. So the formula for the test statistic is going to be t is equal to the sample slope minus what we're assuming the true slope to be. I'll put a little b0 here because it's going to be kind of our null hypothesis, right? Divided by the standard error of the slope. Okay. So value minus the mean divided by the standard deviation, right? Okay. So now, when we do a hypothesis test, it's kind of like a difference in proportions or a difference in means test. This is typically going to be assumed to be 0. All right. So with the significance test for slope, our null hypothesis is no association, which would be a slope of 0. Okay. So typically that value is going to be 0. All right. And so next question is, what is the usual null hypothesis? Well, it's going to be beta equals 0. Okay. All right. And so if there is no slope, if the slope is 0, all right, that would be similar. And if you think way back to the candy grab activity, all right, seems like months ago, maybe it was, that's similar to the idea of just using the mean of the y values, right? So remember we talked about, well, if we just predicted the number of candy you can grab from the mean of the candies grabbed, then that's one way to do it. Is it better to predict that using an x value like handspan? All right, so if the slope is 0, then really that's similar to just using the mean of the y values or the mean of the candy grab to predict candy grabbed. Okay. All right, so that's what we'll assume to be true. What we're looking for is evidence that the slope is not 0. Okay, that it's positive or negative. Okay. All right, so we'll get to the specifics of that here shortly. All right. Let's look at an example. Okay. All right. Many people believe that students learn better if they sit closer to the front of the classroom. All right. So, is there an association to what row you sit in and your grade? So, if we consider row and grade to both be quantitative variables, then we could answer this question about an association using a significance test on slope. Okay. All right. So you see the information here about the association between the two. Okay. As you might expect, and if you look at the R squared value especially, this isn't a real strong relationship, but if you look at the residual plot, it's very scattered, no curvature, no obvious curvature. So a linear model is appropriate. It's just not going to be real strong. Okay. And so they give us a scatter plot here, and they give us a dot plot of residuals instead of a histogram, but again, we'll use that in the same manner. Okay. So that's really all the information we need to proceed with the significance test. Okay. Now, first of all, 1 through 9, these questions are chapter 3 type questions. All right. So again, as a review for describing an association or describing or determining an LSRL from computer output, calculating correlation, all that chapter 3 stuff goes through number 9. Okay. Well, or at least number 7. I think number 8 and 9 you should try to answer as well. Okay. So again, I encourage you to pause, kind of fill that out as review, and come right back. Okay, you're back. Welcome. Okay, let's just look at what this stuff should look like. Okay. Again, the graphs and stuff are hard to see here, but just concentrate on what the answers are. Okay. All right. Obviously, if you look at the scatter plot, it looks like a pretty weak association. If you calculate the correlation in number 3 and you kind of look ahead there, negative 0.21, that's a pretty weak correlation. All right. We've kind of looked at a model where plus or minus 0.5 is the cutoff to go from weak to moderate, and this is 0.2, so that's pretty weak. All right. But really, number 1, you should try to answer based off the scatter plot. So I wrote there as a weak negative linear association. Okay, again, strength, direction, form between the row seated in and the test score. Okay, so row seated in is our explanatory variable. Test score is our response variable. Okay, there you can see the LSRL with the variables defined. Okay, and the slope and y-intercept, again, right off the computer output, there's slope, there's y-intercept. To calculate the correlation, we know it's going to be negative because the slope is negative. So we just take the negative square root of r squared, and that's where we get the negative 0.216. Okay. Remember when you do that, to take the r squared value, which is 4.7% here, and convert it to a number before you take the square root. Okay. When we interpret r squared, we use the percentage, but when we convert it to or when we calculate correlation, we have to convert it back to a number first. So notice that I did the square root of 0.047 to get that. Okay. All right. Some more review. Calculate and interpret the residual for the student who sat in row 1 and scored a 76. Where are we at here? Okay. So again, it's y minus y hat. So the actual value minus the predicted value. So the actual value is 76. The predicted value from the equation is 84.59. So there's your residual. It's negative. So when we interpret it, we say the test score was 8.59 points lower than predicted. Make sure when you interpret a residual to include a reference to the x value in context. So in this case, for a student seated in row 1. Okay. All right. Interpret the slope. That should make sense. It's predicted to decrease because it's negative for each increase in x, one row. Interpret the standard deviation of the residuals. All right, so when using this LSRL to predict test score from rows seeded in, predictions are typically off by 10.07 points. Again, from the computer output, S is right here. Okay, R squared is right here. Okay, so interpreting R squared, I've got the word approximately in there. Okay, and then when we get to number 8, explain why it was important to randomly assign the students to seats rather than letting each student choose his or her own seat. This is a review question as well. Randomization reduces bias or eliminates bias, okay? And we're trying to avoid bias from potential confounding variables that may affect test scores. Again, less confident or prepared students might choose to sit in the back. And that would be a confounding variable that would affect the grade that wouldn't be related to the row that they're sitting in. So we do want to do random assignment just to avoid bias like that. All right. You don't want to have people choose where to sit in an experiment like this. Okay. What other variables did the teacher control here? Well, so it's going to be the same test for each student, same amount of time, same teacher. Test is over the same chapter, etc. So there's a lot of controls when you conduct a test. So a lot of variables that would be associated with those would be eliminated. All right. And all of that control reduces variation or spread. Okay. So when we do spread, that's going to increase our R squared, decrease our S, and also decrease the standard deviation, standard error of the slope. So when you do all that, when you eliminate variation, you make it easier to see the linear model. Okay. All right. So let's look at the hypothesis statements. Okay. So we talked about what the null hypothesis would look like. So our state step would be we want to test the following hypotheses at the alpha equals 0.05 significance level. Okay. Null hypothesis is going to be that the true slope or the slope of the true population line is 0, no association. All right. In the question, going all the way back here, it says, do these data provide convincing evidence that sitting closer causes students? Okay. Now for the causation, we're doing random assignment. We're doing an experiment. So that would satisfy causation. Does it cause students to get higher grades? So does a lower row number cause students to get a higher grade? So in a case like that, the slope would be negative, right? Because as row number goes up, grade goes down. So we're specifically testing here that the slope is less than 0. Okay. If they're just looking for any type of association, then you might use not equal there. Okay. All right. So what's the evidence for HA? Okay. So we're going to include that in our state step as well. Sample slope is negative 1.1171 from the computer output, which is less than 0. 2 explanations. True slope is 0. We got a sample slope less than 0 by chance, or the true slope is less than 0. That's nothing new. Okay. Here is the formula for the standardized test statistic, like we talked about earlier. So if we go ahead and apply that, we will take our sample slope, a negative 1.1171 minus our null hypothesis value of 0, divide it by the standard error of the slope. Okay. So again, that is right next to the slope itself, 0.9472 in this case. Okay. And you get a test statistic. Okay. With a t-test statistic, you use t-CDF to get a p-value. All right. Since it's negative, we're going to treat it like a less than, and our alternative hypothesis is also less than, right? So we'll go from a lower of negative infinity up to an upper of negative 1.179. Our degrees of freedom is 30 minus 2. Where did I get 30 from? Well, there are 30 dots on the dot plot. It does not say in the problem. So that's where I got it. Okay. Typically, you want to count the dots. You would probably be given that information in the problem stem itself. But it looks like, unless you see it, I don't see 30 anywhere. All right. But there are 30 data points. So, so our degrees of freedom would be 30 minus 2. And that gives us a p-value of 0.136, not that low. So since the p-value is greater than any typical alpha, we would fail to reject. There's not convincing evidence that sitting closer causes students to get higher test scores. Or you could say there's not convincing evidence that the slope of the true regression line is less than 0. Okay. All right. Very typical type of significance test for slope. Okay. All right. We are almost done here. Excellent. Okay. All right. So the next thing is, can you use your calculator? All right. And you can if you have the data, but to do a t interval for slope or a t test for slope, you're going to use the calculator, you're going to have the data. And on a typical AP exam question, that's not going to be the case. So this is not something on the AP exam that you would have to worry about, but obviously in real life, if you're trying to do this, you will have the data. So you could simply plug it into your lists, and it makes the do step, as always, a lot easier. Okay. All right. So a couple of notes here on that. Okay. The calculator functions are listed here. It's linreg tint and linreg ttest. All right. If you go to second distributions where all the other stuff is, or I'm sorry, if you go to stat tests where all the other stuff is, you'll see those listed. You must have your data in list 1 and list 2, or in 2 separate lists first to accomplish this or to use this. Okay. All right. Now, with the calculator, okay, again, you're going to need the standard deviation of the residuals, you would think, right? So when you do a linear regression with the data in your lists, it creates a resid list. Okay. If you do one variable statistics on the residual list, you can get S, which is the standard deviation of the residuals for your sample. Okay. All right. And then to get standard error for the slope, here, let me go to a little more readable version of this. So once you get S, if you're doing it this way, okay, so the standard error of the slope, so you can use this here. Let me make this a little bit more clear. So that's a T equals B minus sample B over the standard error of the slope, right? This is the test statistic formula. Okay. All right. So when you do a linreg t test, you can get a t critical value, right? So you'll know T, okay? You'll know the sample slope. So you can use this formula and solve for the standard deviation of the slope, okay? If you need to get that, all right? Okay, so here's an example, all right? So a random sample of 10 U.S. winter athletes, or sample size is 10 here, they tell us that. Is there convincing evidence of an association between height and weight for U.S. winter Olympic athletes? It's probably pretty good evidence for an association between height and weight for just about anybody, all right? But what you can do is, here's the data, okay? So in list 1, we could put the heights because we're, looks like we are thinking height may explain weights. So in list 2, we would put the weights. Those are our Ys. All right. If we do a linear regression then, all right, stat calc 8, that'll give us a formula, an LSRL. So predicted weight equals negative 416.77 plus 8.54 times the height. Like with chapter 3, if you make sure diagnostics are on, it also tells you what the correlation is. And if you square that, that's our R squared value. So we have all that information just from the data. Okay. So if I want to do a significance test, we wish to test the following hypothesis. Again, beta equals 0. Now in this case, is there convincing evidence of an association at all? Okay. Then we could use not equal 0. Okay, because if the slope is positive or negative, there would be an association. Doesn't really matter what's what here, okay, as far as what they're asking. Defining beta, it's the true slope of the regression line relating height to weight, or you could say the slope of the true regression line. That works too. Evidence for HA, if you see from our regression that we did in the calculator, the slope is 8.54, which is not zero. So we do have evidence for HA. If conditions are met, this is a t-test for slope. And then we have to check liner. Now, if you're using the data, you're going to have to create your own plots. And if you look at the bottom of the page, I created a scatter plot, a residual plot, and a histogram of the residuals just on the calculator and just did a rough sketch, okay? Again, I think from this you can see why we're not going to ask you to do this very often, or maybe not at all on a test, because there's so many errors you can make with data entry that screws up your plots and your the equation of your line and all that stuff, that we wouldn't want that to happen. So again, most problems you're going to get from computer output. But my scatter plot looks fairly linear, no obvious curve pattern in the residual plot. Histogram shows no strong skewness or outliers. So with liner, our linear condition is met. Sample size was 10. We can assume more than 100 U.S. Winter Olympic athletes, I believe, in the population. Normal condition, as I said, no strong skewness or outliers in the histogram of the residuals. If you look at the residual plot, the spread of the y values is pretty constant for each x. Give me a minute. Let me bring up an example of maybe where that equal SD condition would not be met, or maybe I can sketch one. Okay. And then the random condition, random sample was stated in the problem. So conditions are met. All right. Now at this point, with the values in our lists, we can do a lin-reg t-test, which will spit out a test statistic, a p-value, and a degrees of freedom. Okay, you just have to make sure your data is in the list and specify the alternative hypothesis. Okay, and then we write a conclusion statement. All right, that is really the only difference when you're using the calculator function. Okay, but again, it's probably not too often that you'll be asked to do this where you're given the data. Okay. All right, let me pause for just a second, and let me find a bad residual plot. Just 1 second here. Okay, I'm on page looks like 744 of the textbook. All right, so the equal SD condition, at the bottom of that page, they show you a good example of where that condition is met versus where it's not. Let me make this a little bigger. So this residual plot's pretty good, pretty equal spread as we go left to right, up and down, above and below the zero line. Here's an example of coning where the equal SD condition would not be met. All right, notice how the spread for these lower x values here, the residuals are a lot smaller than they are for the higher x values. So there's kind of a cone shape you see here. And coning would be a case where your equal SD condition is not met, okay? And if you flip this around the other way, same thing, your equal SD condition would not be met if the spread wasn't equal. So I just wanted to make sure you got an example of that as well. All right. Hey, that finishes up 12.1. For this week, look on Canvas for the homework assignments associated with 12.1. The homework sets, if you look in the notes, are all really small. So we're going to have one homework assignment for 12.1, have a video for 12.2, which is very short assignment for 12.2. And then you're going to be on test review mode for a test that we'll conduct next week. All right. If you guys have any questions on this, let me know. Good luck. And we will talk or email or Zoom or something like that soon. See you.